Hi, I'm Mark Weitzman, and welcome back to our third video in this sequence of videos on a deep dive on the chi-squared and student t distributions. And the independence of the sample mean and sample variance. And as I've previously stated, all of this is adapted from, by the way, when I say it's adapted from, the problem is Matthews and Walker, the solution is mine. So any errors or any errors in the solution or on this video are my fault, not the book's. Problem 14.7. So previously we figured out what the chi-squared distribution is for d degrees of freedom, and we analyzed the behavior of IID Gaussian variables under a orthogonal transformation. And now in this video, okay, we're going to use what we did in the last videos, and we will we'll actually show the independence of the sample mean and sample variance. So what we're going to do is we're going to define an orthogonal transformation M such that y1 is equal to the square root of 1 over n times x1 plus x2 plus dot 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 xn. And this also is equal to the square root of n x bar. You divide by the square root of n, you'll see that. It's the same as x bar is equal to 1 over n x1 plus dot 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 xn. And I'm also going to define a sample variance. I'm going to leave out the 1 over n minus 1 factor. It's not important for what we're doing in this video. I'm just going to define it as the sum of the squares between the mean, the sample mean, and the variables squared. Okay, and we have to show, x bar and s are independent. Now, this orthogonal transformation M, as long as we get the first variable right, we don't care how we define the rest of it. It just has to be orthogonal. So this is easy to do. And let me define a few vectors to make everything a little bit clearer. So the vector x as a vector just has components x1, x2, up to xn. And the mean vector x bar x, we're just going to define this as having all components the same, just x bar, and x bar. So it's one vector, and it's all of its components are the same. As I said, the only thing we require is that y1 equal mij xj. And the rest of so this basically means that the matrix M has the form square root of 1 over n, square root of 1 over n, dot, 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 square root of 1 over n. And then the rest of it, we don't care what it is. It just has to be orthogonal. And that's easy to accomplish. Now, the basic property, which I won't establish here, but it's easy to establish, and maybe you should go do it if you haven't seen this before, of an orthogonal transformation is that the norms of vectors are preserved. And if you think of what an orthogonal transformation is, it's either a rotation or an inversion. It could be a reflection. So it's kind of obvious from a physical point of view why the norms are preserved. But it's easy to establish using the basic property of orthogonal transformations. M transpose M is equal to the identity transformation. So we're going to use this property on several vectors to show that the mean and the sample variance are independent. So based on these definitions, the norm of the mean vector is equal to, it's just the square root of x bar squared plus x bar squared plus x bar squared. There's n of them, so it's the square root of n times x bar squared, which is equal to the square root of n x bar, which is equal to y1. Okay. Now, let's apply m. Let's take the norm of m times that same vector. Well, let's apply the transformation m to our mean vector, x bar, x bar, x bar, x bar. First one's just going to be 1 over the square root of 1 over n times x bar. Everything's the same. It's just going to be n of these things, so it's the square root of n times x bar. We've already established that that's y1. The rest of these components, I have no idea what they are, and I don't care. I'm just going to call them y2 prime all the way up to yn prime. Prime means it's the component gotten from applying the transformation m to this mean x bar vector. Okay, but we know that the norms are preserved, and the norm of x1 is y1. Let's write the norm. I'm going to write okay, so this, we know that this has to be equal to y1, but it's also equal to, from this thing, the square root of y1 squared plus y2 prime squared plus dot 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 yn prime squared. So this implies, since these are positive numbers, the only way this can happen is if y2 prime equal y3 prime equal yn prime equals 0. So that's one thing we've established. Now let's take a look at the the norm of x minus the mean vector. Let's take its square. So, since this is x and this is the mean vector, we just subtract the components and square each one. So this is x1 minus x bar squared plus x2 minus x bar squared, xn minus x bar squared. And this is what we've defined as the sample mean, sample variance. So we have that. Now this has to be equal to the norm of m times that. Squared. Okay. Well, we know what mx is. We worked that out over here. Actually, we didn't. We just define. I wrote m, and m gives y1, and then it gives y2, and up to yn. So this is just y1, y2, yn. I'll put this as a norm. It's this vector minus, we did work out what mx bar is. That's where these all come into 0. This is going to be y1, 0, because y2 prime is 0 all the way up to yn prime. So we get all zeros up to here squared. So this is equal to the norm of the vector 0, y2, yn. That's simply equal to y2 squared plus y3 squared plus ... yn squared. Remember, we've shown, since the norms are preserved, this has to be the same as this, so this has to be equal to s. So this is like a nice formula for s. Now, we're practically done, because we know that the mean x bar is equal to 1 over the square root of n times y1. So clearly, okay, and from the previous video, we showed that all the y's are independent. We showed they're independent if the x's are independent and they rise, and the y's arise from an orthogonal transformation. So all the y's are independent, and now we've shown, because s depends on y1, yn, I'm sorry, y2 up to yn is clearly independent of y1, which is proportional to x bar. So s and x bar are independent random variables. I'll stop here, and in the next video I'll get the distribution of s and x bar, not too difficult, and s will essentially have a chi-squared distribution, and then in the following video we'll do the hard work and get the Students T PDF. Thank you very much.